I wanted to come up with a voice module that would tell when the crossband 2-meter radio is on a particular frequency, and it could voice it out over the 440 crosslink. I found these modules on eBay. They use a chip called the YX5300 UART controlled MP3 music player. As you can see, they're pretty low cost. So I ordered 3 of them at $287 from China. It took 6 weeks for them to come in. What I really wanted was not the board, but just the chip. Could not find anyone selling just the IC itself. So I had to remove the IC and come up with my own board for the circuit. I found a data sheet online for the IC YX5300. However, it needs translation. As typical for many of these chips, they're in Chinese. There is some English here, but not enough information really to tell you what's what. You can tell what pin goes to what, but what each pin does is not very clear. So I had to dig around on the internet for a few more details on the IC itself and how to program it. Even the pre-manufactured board from China didn't have a lot of information available for it. I found this information from Catalec's Serial MP3 Player Manual. It pretty much looks like the one I ordered from China online. It has the same printed circuit board shown here. However, the programming was still a little vague. It does give quite a few specifications, does explain the PCB layout and some of the indicators, jacks, and so on, and the command structure for sending commands to the audio processor chip via the UART interface, such as volume up, volume down, set volume, single cycle play, on and on here. Connections, how to connect using a USB serial adapter from a PC shown here. This is an example of the command structure, which took a while to decipher. It did give the baud rate, however, 9600, so that was good information. These are send commands. They didn't tell what each command was here. I deciphered these commands on this sample programming sequence sheet. Command 1, select storage device, which would be the SD card in this case. Command 2, play first track. Command 3, set volume. Command 4, play, and Command 5, pause. So these are some of the commands I can experiment with to place into the chip to see if anything's going to happen, and maybe at least get started on figuring out how to get this chip to take data and actually produce sound out of it. I had to trace the board out, so I removed all the parts on one of the modules and traced it out to draw up a schematic so I could make my own board and interface it directly to a microcontroller that will interface to the repeater controller. After tracing out the printed circuit board, this is the schematic I came up with of the board itself, and I'm going to use this schematic to generate a schematic with a microprocessor interface for the repeater controller. Here's a view of the speech processor schematic I derived from the handwritten schematic by going through the original printed circuit board, which is mainly this section here. This is the SD card. Here's the speech processor, and I'm using a C8051F381 processor. One of the things I needed was 2 UARTs on the processor, one to drive the speech processor and one coming from the repeater controller with the data. So there's actually 2 UARTs here. Audio left and right, I just summed them. And then here's a playback level, and audio voice comes out of this header here. Of course, the power supply, 5 volts down to 3.3. Both of these ICs operate at 3.3 volts. The speech processor board will plug onto the repeater controller. It goes here on J402 for the voice module. These are the wave files I had to create for the speech processor. Each file corresponds to the number that is displayed on a particular segment of the 7950 2-meter radio that I'm using for crossband on the repeater. So in software, I need to decode the segments of the readout and play these files according to what the segment shows in order to read out the frequencies. These are the individual files that have to be chosen each time a segment is read out.
1, 2, 3, 4, 5, 6, 7, 8, 9, 0, point, minus, plus, simplex.
40. So these are the speech files that I have to write software for to give the frequency of the 7950 and get them to come out in the correct order. I put together some code in assembly language here for the C8051F381. The chip is from Silicon Labs. We're going to try to program this YX5300 audio controller chip. Come up with some locations here, AMUX 0 through 7. What those locations are is each one of these commands, it takes 8 bytes per command. So we have all 8 of these, which will be loaded into these locations. These display locations are storage for the 7950 display data that comes in on the serial port. So this is the serial data that'll get loaded into the speech processor. Here's those AMUX locations. If you look at this, 7EFF for the first 2 bytes, and then the last byte's an EF. So those are always consistent. So they will always be loaded here into AMUX 0, AMUX 1, AMUX 7. This is the data start code. This is the data end code. And every sequence has that. So here we load SD card. We select SD card, just like over here. Select storage device, so it's 06, 09, 00, 00, and 02. And same here, 06, 09, 00, 00, and 02. Set volume, then select track. In select track, the example shows play first track, which is this 01 here. So this byte is the one that tells which track to play off of the SD card. Location 6 here of the select track program location is where we inject the wave files. And these are numbered 01, 02, 03, 04, 05, and so on. And that is what this SQDAT is. And that in another section is loaded with the particular display data from the 7950 that is sequenced into this 6th location. And then the next command is play audio file. So now we go down below to the subroutines. This is the ASCII data coming from the 7950. And we have to decipher this, and that SQDAT showed earlier. If I put 01, that is track 1 here. And the audio will say 1. So move audio number 1 into SQDAT, which in this byte, play first track would be 01. So if there's a 1 selected, it would load this in the SQDAT. SQDAT being this location, which is placed into location 6, data byte number 6 going to the speech processor. And all through this code, we look for the number coming in from the 7950 and convert it to an audio file number, and then it's played. Okay, we're doing some preliminary testing here.
1.49 simplex.
Some of the numbers are not sequencing quite right.
43.4122.
Probably a timing issue with the serial port or so on. But it's something that we can work on.
143.4122.
Yeah, we'll work on that when we get a PCB.
143.412.
But it looks like it's a go. So we'll go ahead and lay out a printed circuit board. Okay, I've got a PCB layout made for the speech processor circuit shown here. The board is 2.4 inches by 0.6 inches, and it needs to fit on the main repeater controller right at this header. So between this standoff and this header, that board needs to fit in here. So it's kind of a long, skinny board because it has to clear this capacitor. And there's another daughter board here that it also has to clear. So the board ended up being this size here. On the bottom of the board is the SD, shown in yellow here, silkscreen at the bottom of the board. Yet the SD card socket is right here. Microcontroller, speech processor IC. Down here we have option pins, which I haven't assigned to anything yet. They're just spare pins for now that can be assigned in software. And programming header right here for programming the micro. And the I/O port, which goes down to the main board. So we're ready to generate Gerber files and order boards. Okay, now I'm removing the sound chip from one of the boards, from one of the audio boards, so I can put it on the board I just got from the manufacturer. And in kind of fast motion here, going to mount a couple of these surface mount chips. As you can see, I'm using the Kester Flux, which works really well for this. This is the microprocessor, so we're going to mount that next. Always mount the surface mount chips that are fine pitch pins first, because other parts can tend to get in your way, and then it's really hard to get these on there. So it's best to do the surface mount chips first, especially if they're got very, very small pin outs. And once the chips are mounted, kind of take a Q-tip and some 91% isopropyl and just kind of clean up some of the rosin from around the pins. Later on, the whole board will clean with isopropyl alcohol. As I build the boards, I usually mark off the bill of material one part at a time, just to double check that, to make sure all the parts measure up to what the bill of material says. And I also mark off the assembly drawing. Once most of the parts are mounted on the board, I'll clean it with 91% isopropyl alcohol. This gets all that rosin off that I used to mount the parts on, and it makes a nice clean board. After the alcohol, you soak it in distilled water and then dry it with a heat gun. And that gets most of the water out from underneath things, and then you get a nice clean board. Potentiometers, connectors and such you add later, because you don't want the alcohol and the water to get down inside of these parts. So those have to be added later, and the best you can do is take a swab of alcohol and clean it up with that. So now we're mounting the connectors and so on. This is the SD card connector that we're mounting now. And you don't want any fluids, alcohol or water to get in that either, so that's one of the last parts to mount. I'm not even using any rosin to mount this part because of contamination that could get into the contacts. The one contact I missed there is a no connect, so I didn't bother to solder it. Now we're going to test the voice module on the repeater controller.
146.550 simplex.
It's kind of hard to see the readout the way the illumination is.
146.715 minus.
So I'll move it over to the 7950 so you can see the readout.
146.880 minus.
So the voice module is decoding the frequency that's sent via serial port to the controller.
147.090 plus.
To the repeater controller. And the segments are taken via software and turned into voice.
146.520 simplex.
And you can use anyone's voice to make the voice files for this.
146.685 minus.
So another part of the repeater controller has been completed. So the crossband 2 meter, you'll be able to tell what frequency it's on by a touch tone code on the 440 radio.